Okay, so now let's take a look at how we can visualize an optimization problem. Let's start very gently with an optimization problem in two-dimensional, meaning that we have to design variables. Let's say we want to minimize f of x, which is our objective function, equals to x1 cubed plus 2x1 x2 squared minus x2 cubed minus 20x1. And it is with respect to our design variables x that takes the bounds from -5 to 5. And there are also two constraints. First one is g of x, our inequality constraint, minus x1 minus x2 minus 3 less than or equal to 0. And another one is the equality constraint, which is h of x equals to x1 minus x2 minus 1.5 equals to 0. Because this problem has two design variables, meaning that it is in two-dimensional, there are actually two ways to visualize this problem. We can either visualize it as a 3D surface plot, where you can see in here we have x1 and x2 at the bottom. So these are the design space. This is the design space. And this surface essentially gives you the objective function. As you can see here in the height, the f objective function is basically visualized in the z-axis, the height axis. You can see for the surface point that is higher, it means that its objective value is higher as well. So I can zoom into some of the points on this surface, and you should see that a tooltip over there giving me the values of the point of that surface. In here, x is around minus 0.3, y is around 3.5 or 3.6, and the z value over there is around minus 39 something or minus 40. So that gives you, for each point in the xy space or x1, x2 space, a corresponding f value. So for whatever x1 or x2 you choose, that will be a corresponding value of the objective as shown on this surface here. So you can immediately tell the shape of this function and where it is potentially a minimum or a maximum. Now, the other way to visualize it is by a 2D contour plot in here. You can think of it as like the 3D surface plot being projected onto a 2D plane, so being squashed down into two dimensions. So if I tilt it like so, you can see that it resembles this plot over here. So viewing from top to bottom in an overall view, you can see the surface, although it's a little bit warped, but when you flatten it onto a plane surface, then it will look something like this. Now, in a contour plot, we have different colors that represent different values of the objective function. And the color scale that I've chosen in here is the RDBU reversed scale, so red and blue. But in the sense that it's very intuitive, where blue meaning is cold, meaning is low value, and red meaning is hot value. So you can very intuitively see from the plot over here, values or points over this area would be of a low objective value, and points over this region here would have a very high objective value because it has a very red color. So the redder it is, the higher value it is for the objective function, or the bluer it is, the objective value will be lower as well. You can also see a corresponding color scale in here, where the values go from minus 400 to 400, and the hotter it is, or the redder it is, we have a higher value for the objective value. And we also have the contour lines. Here, the contour lines, I have also annotated it with the values. You can see, for example, this line here, it has a value of 20, meaning that any point on this contour line will have an f value of 20. So they have the same objective value every point on this line. And similarly for this line over here has a value 0, meaning that all of the points on this line will have an objective value of 0. And because of the way that we plot all of these contour lines, whenever the contour lines are more densely populated, whenever they're more squashed towards each other, it means that the rate of change is greater and greater. So it's faster and faster to get from minus 40 to minus 60 to minus 80 and so on. You can also see here that the kind of slope or the gradient is dropping more and more rapidly. So it's dropping more fiercely, contrasted to some other regions where it's flatter, something like this region over here, zoom in closer, you can see the contour lines are not as squashed towards each other. So you can build your intuition around how you can go from a 2D plane plot to a 3D surface just by imagining things like this. Now, because this problem is a minimization problem, this means that we want to find a point where the value is minimized. So in here, you can tell, because we want to have a value that is as low as possible, where all of the other directions around it are increasing. So we can actually see the minimum is over here at this point. Now, this minimum point has the characteristic that it is at the bottom of a valley. So if you want to find the minimum value or the solution to the minimization problem, look for valleys, and the lowest point at that valley would be the answer. This is the intuitive way of thinking about minimization problem. If the problem instead is a maximization problem, then basically it's the other way around. You want to look for a hill, and the top point on that hill, or something like this in the red area here, because red is higher, right? So we want to go to this point because it's the top of a hill. This means that it is the solution to a maximization problem. Instead, we'll go into more mathematical or more formal definition of an optimal point in part 4, where we talk about gradient-based methods. But to build up your intuition, an optimal solution would not be somewhere over here or somewhere over here. It would actually be a signature point that is at the bottom of valley, where all of the directions around it point uphill. So now let's take a look at equality and inequality constraints. Equality constraint is plotted as a line in our surface plot because it means that the line as specified by this h of x equation has to hold true. So all of the points that rest on this line can be a feasible solution, but any other points where this line does not hold, meaning the points that are not on this line, cannot be a feasible solution. So it's a very restrictive constraint, and it only allows you to choose points that lie on this line to be an optimal solution, to be a feasible solution. For inequality constraints, we typically plot it as a shaded region, meaning that anything within this shaded region are not feasible. So a feasible solution must be a solution that is outside of this shaded area. So you can imagine all of the points here would be a feasible solution to this inequality constraint. And this inequality constraint is given by this particular equation over here, minus x1 minus x2 minus 3 less than or equal to 0. Very intuitively as well, if this inequality constraint is actually greater than or equal to 0, this shaded area would actually just be flipped to the other side. So this side instead will be infeasible, and this side instead will be feasible. So this is how you can imagine or visualize inequality or equality constraints. Now, what about the minimum that is actually the solution that we want to look for? Because right now, this minimum here is not a constraint minimum, it's a minimum solution to the problem without these two constraints. However, our optimization problem actually has two constraints here, and the solution has to be on this line, and it also has to be on this section of the line because it cannot go into the shaded region. So have a think about it in 5 seconds. Where do you think the new optimum, the constrained optimum, will actually be? Okay, so if your answer is somewhere here, then congratulations, you are correct. Now, why is this our actual solution? Because geometrically, the constrained optimum would want to be as close to the unconstrained optimum as much as possible so that it can get to the lowest value as possible. But because it is constrained, so you can think of it as trying to pull this point towards this particular unconstrained minimum, but you have to still stay on the line of this constraint, then naturally this constraint optimum cannot be a point over here, or it cannot be a point over here. It must be a point that is closest to the unconstrained minimum, the black diamond symbol over there, instead of any other places on that constraint line. So that's why, geometrically speaking, the constrained optimum will be the closest point to the unconstrained one while remaining on the constraint line. And this is how you can visualize optimization problems. We're going to look at some examples later on where you can interact with it yourself as well. But again, it's very important that you let this intuition sink in and build up in your mind so that you can see the different problems, how you can actually spot the optimal solution or the constraints, whether there's something that might not be set up correctly. Once you have this intuition, it becomes second nature to define optimization problems and run them effectively and efficiently.